Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this circle. In the second question, we'll find out the area of this trapezoid ABCD. So we'll start with the first question. In the drawing we have a circle, and this is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we have the right triangle ACP. The right triangle ACP cuts the circle at 2 points. Point A and this point. This angle equals to 90 degrees in its size. Side PC of the right triangle ACP equals to 4 units in its length. This is side BC, that is equal to 1 unit in its length. Our mission is to find out the area of this circle. So first of all, we can implement here rule 2. So click quickly on rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. So in the drawing we have a circle, and this is the common start point P. From this common start point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, we have the common start point P. From this common start point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So I write it down. According to rule 2, tangent PA equals to tangent PB. It is given us the question that the length of tangent PB, the length of this tangent PB, in total it is equal to 4 plus 1, that is 5. So write it down. PB equals to 5 units in its length according to what is given in the question. And for this equation, PB equals to 5, we will derive that the length of tangent PA is also 5. So PA equals to 5. So here PA equals to 5 units in its length. In the next step, I'll copy the right triangle APC in a new point, and we will implement the Pythagoras theorem on this right triangle APC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle ACP that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. So I write it down. AP squared is equal to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equal to AC squared. AC is the missing side, so we leave it as it is. AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and we get that 25 minus 16 is 9, so 9 equals to AC squared. Here we take a root out of this equation, and we get that the missing sign AC is equal to the square root of 9, that is 3. So AC equals to 3 in its length. This is the missing sign AC, that is 3. So come right here, that this missing sign AC is equal to 3 in its length. AC equals to 3. In the next step, we define the center of this circle. This point is point O, and we'll also define the radius of this circle as x. In the next step, we'll join points O and B together by a straight line. So what is the definition of line segment OB? Line segment OB starts from point O, that is the center of the circle, and ends at point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore OB is the radius of this circle, that is equal to x according to our definition. So here we can implement rule 1. I'm just clicking on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB. This is tangent AB, that is tangent to this circle at this point, point M. In addition, we have also the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OB, that is equal to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And now your radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point C, here, so here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees. So which angles we have at the upper side of PB at point C? we have this angle that is a right angle plus this missing angle. In total, the sum of those two angles, they must be equal to 180 degrees. So this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction. That is to say, from this point O, that is the center of the circle, we will draw perpendicular on AC. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We will define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can do the quadrangle OECB. Inside quadrangle OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle not a square. So we relate to this quadrilateral OECB is rectangle because it has 4 right angles. So I write it down. This quadrilateral OEBC is rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side BC must be equal to the opposite side OE. But BC is 1, therefore OE must be also equal to 1. Likewise, according to the sum rule, in the same rectangle OECB, side OB must be equal to the opposite side EC. But OB is x, therefore EC must be also equal to x units in its length. What is the length of the missing 97 AE? From the drawing, it is very easy to see that AE equals to AC minus EC. Again, AC minus EC equals to AE. So I write it down. AE equals to AC minus EC. So AE equals to AC, that is 3, minus EC, that is x. So in total, A equals to 3 minus x units in its length. So write it down. A equals to 3 minus x units in its length. In the next step, we will join points O and A together by side line. OA is of course the radius of this circle, that's equal to x according to our definition. In the next step, I'll copy the right green triangle OAE in a new page, and we'll implement the Pythagoras theorem on this right green triangle OAE. Here by PT is abbreviation for Pythagoras theorem. So here, this is the right green triangle OAE that comes from the original drawing. According to the Pythagoras theorem, in this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to AE squared plus ED squared. Again, OA squared, that is the square of the hypotenuse, equals to AE squared plus EO squared. So I write it down. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. The hypotenuse AO is x, therefore AO squared is x squared, and it is equal to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. Plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total we found out that x squared equals to 3 minus x squared plus 1. Here we'll open the brackets on this side of the equation, and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After I cancel x squared, on this side of the equation we are left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we found out that 0 equals to 10 minus 6x. Here we'll add 6x to this equation, and we get that that 6x equals to 10. So here we divide this equation by 2, and we get that 6x over 2 is 3x, and 10 over 2 is 5. So 3x equals to 5. Here we divide this equation by 3, and finally get that x equals to 5 over 3 units in its length. So we actually found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So write it down. The area of any circle is equal to pi times the radius of the circle squared. So the area of our circle will be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total we found out that the area of this circle is equal to pi x squared. So it is equal to pi times x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total we found out the area that we are looking for, that is the area of this circle, is equal to 5 times 3 equals to pi times 5 over 3 squared. That is to say, it is equals to pi times 5 over 3 squared. And 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total, we actually found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So repeat again, we found out that the area of this circle is equal to either 25 pi over 9 square units, or in terms of numbers, the area of this circle is equal to 8.727 square units. So we finish with the first question. In the next step, I will present you the second question and we'll solve it. Our mission in the second question is to find out the area of this trapezoid ABCD. So it is given as the question that side AB of this trapezoid ABCD equals to 16 units in length, AD equals to 17, BC equals to 25, and side DC of this trapezoid ABCD equals to 44 units in its length. Again, our mission to find out the area of this trapezoid ABCD. So first of all, we know that the area of any trapezoid is equals to the sum of its parallel sides times the height over 2. So I'll write it down. The area of trapezoid ABCD will be equal to the sum of its two parallel sides. The two parallel sides are AB and DC. And the sum of the two parallel sides, so of course, is AB plus DC. So it is AB plus DC. It is the sum of the two parallel sides times the height over 2. We define the height as h, evaluation for height, divided by 2. And the height must create 90 degrees with the two bases AB and DC. So the area of trapezoid ABCD is equals to the sum of its two parallel bases, this is AB plus DC, times the height over 2. In order to find out the area of this trapezoid ABCD, we will do a construction. That is to say, from this point A, we draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A in DC, this point, as point E. We will define the length of this line segment DE as x. We will define the length of this line segment AE as h. AE that is equals to h is also the height of trapezoid ABCD. Why AE is the height? Because of the fact that AE creates 90 degrees with the base DC. Again, AE is also the height of trapezoid ABCD. So the height of trapezoid ABCD equals to h, according to our definition. In the next step, I will copy the right triangle ADE in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle ADE. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle ADE that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle ADE, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. So I write it down. This will be equation 1. AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. The hypotenuse AD equals to 17 units in itself, therefore AD squared is 17 squared, that is 289. And it is equal to AE squared. AE is h, therefore E squared is h squared, plus DE squared. DE is x, therefore DE squared is x squared. So in total we found out that according to equation 1, h squared plus x squared equals to 289. In the next step, we will do another construction, that is to say, from this point, point B, we will go perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point F. It is given us a question. Actually, we know that ABCD is a trapezoid, and therefore side AB is parallel to side DC. And those two angles, they are both located between the parallel lines AB and DC. And therefore, those two angles, they are both defined as an interior angles, because they are located between the parallel lines AB and DC. In addition, those two angles, they are both located on the right side of the straight line AE, and therefore they are both defined as one-sided angles. So in total, those two angles, they are both defined as one-sided interior angles. And here we can implement Rule 16. Rule 16 talks about one-sided interior angles. Okay, check Rule 16. According to Rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B. Line I cuts the two parallel lines A and B. Those two angles, that is to say angle 4 and angle 5, they are both defined as one-sided interior angles, and therefore the sum of those two one-sided interior angles is equal to 180 degrees. Here, angle 4 plus angle 5 equals to 180 degrees according to this rule, Rule 16. Likewise, those two angles, that are angle 3 and angle 6, they are both defined as one-sided interior angles, and therefore according to this rule, Rule 16, the sum of those two angles is equal to 180 degrees. Here, angle 3 plus angle 6 is equal to 180 degrees. Angle 3 plus angle 6 is equal to 180 degrees, according to this rule, Rule 16. So here we can implement Rule 16 in our drawing, because we already found out that those two angles are both defined as one-sided interior angles, and therefore according to Rule 16, the sum of those two angles is equal to 180 degrees. So I'll write it down. This angle is a right angle, this is to say it is equal to 90 degrees in its size, plus this missing angle, that is actually angle BAE. According to Rule 16, the sum of those two angles that are defined as one-sided interior angles is equal to 180 degrees. repeat again. 90 degrees plus the missing angle BAE, in total it must be equal to 180 degrees because both those two angles, they are defined as one-sided interangles, and according to rule 16, the sum of two angles that are one-sided interangles is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that the size of the missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle BAE that is equal to 90 degrees according to rule 16. So we actually found out that inside quadrilateral ABFE we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABFE we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must meet its rectangle plus a square. So we relate to quadrilateral ABFE is rectangle because it has 4 right angles. So write it down. Quadrilateral ABFE is rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 units in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side FB. But AE is 8, therefore FB must be also equal to 8 units in its length. What is the length of the missing line segment FC? From the drawing it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus EF. So I write it down. FC in total is equal to DC minus DE minus EF. So FC is equal to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC equals to 44 minus 16 is 28. So in total, this expression equals to 28 minus X. So if we found out that FC is equal to 28 minus X units in its length. In the next step, I'm copying the right triangle BFC in a new page, and we'll implement the Pythagoras theorem on this right triangle BFC. Here by PT is a version for Pythagoras theorem. So actually this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. So I write it down, which will be equation 2. BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. The hypotenuse BC is 25, therefore BC squared is 25 squared, that is 625. And it is equal to BF squared. BF is 8, therefore BF squared is 8 squared plus FC squared. FC is 28 minus x, therefore FC squared is 28 minus x squared. So here we'll open the brackets on this side of this equation, equation 2, and we get that according to this equation, equation 2, 625 is equal to 8 squared, and here plus 28 minus x squared. 28 minus x squared is equal to 28 squared, that is 874 plus x squared minus 2 times 28 times x is minus 56x. So here we subtract 625 from this equation, equation 2, and we get that this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 8 squared plus x squared minus 56x, and 874 on 625 is equal to 159. So in total we found out that according to equation 2, 0 equals to 8 squared plus x squared minus 56x plus 159. Here we add 56x to this equation, equation 2, and we get that 0 plus 56x is 56x, and it is equal to 8 squared plus x squared plus 159. Okay, again, in total we found out that according to equation 2, 56x equals to 8 squared plus x squared plus 159. Okay, so we have already found out that according to equation 1, according to equation 1, 8 squared plus x squared equals to 289. Therefore, we can substitute 8 squared plus x squared in this equation, equation 2, by 289 from equation 1. We do it now, and we get that according to equation 2, 56x equals to 8 squared plus x squared is 289 plus 159. So in total we found out that 56x is equal to 159 plus 289 is equal to 448. So here we divide this equation 2 by 56. And finally we get that x equals to 448 over 56 is 8. So x equals to 8 units in its length. Okay. And again, I found out that x equals to 8 units in its length. According to equation 1, x squared plus h squared equals to 289. And we found out that x equals to 8. If x equals to 8, it means that x squared is equal to 8 squared, that is 64. So we substitute x squared in this equation 1 by 64, and we get that x squared is 64 plus 8 squared is equal to 289. Here we subtract 64 from this equation 1, and we get that 8 squared equals to 289 minus 64 is 225. So if we found out that 8 squared equals to 225, here we take a root out of this equation. Finally we get that 8 equals to the square root of 225, that is 15. So 8 equals to 15 units in Islam. Our mission is to find out the area of this rectangle ABCD. And we've already found out that our mission is to find out the area of this trapezoid ABCD. And we already found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually AB plus DC times the height, that is A, over 2. So the area of trapezoid ABCD is equal to AB, that is 16, plus DC, that is 44, times the height H, that is 15, over 2. 16 plus 44 is 60. So we have 60 times 15 over 2. 60 over 2 is 30. So in total this expression equals to 30 times 15. That is 450. So if we found out that the area of this trapezoid ABCD is equal to 450 square units. And that is the answer to the question. I fill again. The area that we are looking for, that is the area of this trapezoid ABCD, is equal to 450 square units. We finished with the second question. Next step, I'll summarize the lecture. We start with the first question, of course. In the first question, our mission is to find out the area of this circle. So in the following, we have a circle, and we have the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. In addition, we also have the right angle ACP. The right angle ACP cuts the circle at 2 points, point A and this point. This is a right angle, angle ACP equals to 90 degrees inside. In addition, we know that side CP of this triangle, the right angle, side CP of the right angle ACP is equal to 4 units in its length. This is 97 BC, that is equal to 1 unit in its length. Again, our mission is to find out the area of this circle. Okay, so in the first step we implemented here rule 2. If we focus on this common standpoint point P, from this common standpoint point P, we have two tangents to the second, tangent PA and tangent PB, and according to rule 2 they are equal to each other. That is to say PA equals to PB. Okay, again, according to rule 2, the length of tangent PA is equal to the length of tangent PB. But it is given as a question that PB in total is equal to 4 plus 1, that is 5. So I can write here that PB equals to 5. And from this equation, PA equals to PB equals to 5. Then we have that PA is also equal to 5 units in itself. So here PA is equal to 5. In the next step, I copied the right triangle ACP in a new page and we implemented the Pythagoras theorem of this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. So this is the right triangle ACP that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. Again, AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and it equals to AC squared. AC is the missing side, so we leave it as it is. Plus CP squared. CP is 4, therefore CP squared is 4 squared, it is 16. So in total we should find out that 25 equals to AC squared plus 16. Here we subtract the 16 from this equation and find out that AC squared equals to 25 from 16 is 9. So AC squared equals to 9. Here we took out of this equation and find out that AC equals to the square root of 9, that is 3. So AC equals to 3 units in itself. Yeah, this line 7 AC is equal to 3 units in itself. AC equals to 3. In the next step, we define the center of this circle. This point is point O, and also define the radius of this circle as x. In the next step, we join points O and B together by a straight line. OB is of course the radius of the circle, is equals to x according to our definition. PB is a tangent to the circle, so PB is a tangent, it is absolutely a straight line. If you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we joined points O and D together, but actually we did a construction. That is to say, from this point O, that is the center of the circle, we draw perpendicular on AC. Again, from point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, create a quadrilateral AECB inside quadrilateral. Okay, that's quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at this rectangle plus a square. So we relate to quadrilateral OECB as a rectangle because it has 4 right angles. Okay, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side CB must be equal to the opposite side OE, but CB is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side CE. But OB is x, therefore CE must be also equal to x. What is the length of the missing line 7 AE? A equals to AC minus EC. So AE equals to AC minus EC. So A equals to AC, that is 3, minus EC, that is x. So in total, A equals to 3 minus x. The next step, we join points A and O together by a straight line. AO is the radius of this circle. That is equals to x according to our definition. In the next step, I copy the right triangle OAE, the right green triangle OAE in the new page and implemented the Pythagoras theorem of this right green triangle OAE. Okay, this is the right triangle OAE that I copied from the original drawing, according to the Pythagoras theorem. And this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to OAE squared plus OE squared. The hypotenuse AO is x, therefore AO square is x square, and it is equal to AE square. AE is 3 minus x, therefore AE square is 3 minus x square, plus OE square. OE is 1, therefore OE square is 1 square, that is 1. So in total we found out that x square equals to 3 minus x square plus 1. Here we open the brackets on this side of the equation and we found out that x square equals to 3 minus x square. 3 minus x square equals to 3 square, that is 9, plus x square minus 2 times 3 times x, that is minus 6x plus 1. Here we have x square on both sides of the equation, so x square will get cancelled. After we have cancelled x square, inside of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we shall find out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and finally found out that 6x equals to 10. Here we divided this equation by 2 and finally found out that 6x over 2 is 3x and 10 over 2 is 5, so 3x equals to 5. Here we divided this equation by 3 and finally found out that x equals to 5 over 3 units in its length. So we found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. The area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius square is x squared. So, in total, we found out that the area of the circle is pi x squared. But x equals to 5 over 3. X equals to 5 over 3, therefore x squared will be equal to 5 over 3 squared. So in total, the area of the circle is pi times 5 over 3 squared. So it is pi, and 5 over 3 is 5 squared, that is 25, over 3 squared, that is 9. So in total, we should find out that the area of the circle equals to either 25 pi over 9 square units, so in terms of numbers, the area of the circle is equal to 8.727 square units. We finish with the first question. The next time I will present to you the second question and we solve it. In the second question, our mission is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to 16, AD equals to 17, BC equals to 25, and DC equals to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. The area of any trapezoid equals to the sum of its two parallel bases times the height over 2. Repeat again. The area of any trapezoid equals to the sum of its two parallel bases times the height over 2. Therefore, the area of this trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height, that is h over 2. And again, the area of trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height h over 2. The height h must create 90 degrees with the two parallel bases AB and DC. In order to find out the area of this trapezoid ABCD, we did a construction. That is to say, from this point, point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in DC. This point is point E. In addition, we define the length of this line segment DE as x, and we define the length of this line segment AE as h. AE is also the height of trapezoid ABCD. Why AE is the height? Because of the fact that AE creates 90 degrees with the base DC. Therefore, AE is also, AE that is equal to x is also the height of trapezoid ABCD. In the next step, I call the right triangle AED in a new page and implement the Pythagoras theorem on this right triangle, triangle ADE. This is the right triangle ADE that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ADE, AD square equals to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, plus AE squared, plus AE squared. A is h, therefore E squared is h squared, plus ED squared. ED is x, therefore ED squared is x squared. So in total we should find out that h squared plus x squared equals to 289. This is according to equation 1. In the next step, we did another construction. That is to say, from this point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point B in DC. This point is point F. So here we have, we know that AB is parallel to DC. And those angles are located between the parallel lines AB and DC, and therefore they are defined as interior angles. And those two angles, they are both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So those two angles, the sum of those two angles must be equal to 180 degrees according to rule 16. So this is a right angle, and this is the missing angle BAE. So in total, the sum of those two angles must be equal to 180 degrees according to rule 16. So here, the right angle plus the missing angle BAE, in total, they must be equal to 180 degrees according to rule 16. Here we subtracted 90 degrees from this equation, and finally found out that the side of the missing angle BAE is equal to 180 degrees minus 90 degrees, that is 90 degrees. This is the missing angle BAE, that is equal to 90 degrees in its size. So actually, inside quadrangle ABFE, we have 1, 2, 3 right angles. The sum of, we have 1, 2, 3 right angles. This angle equals to 90 degrees according to rule 16. This angle equals to 90 degrees according to our construction. This angle also equals to 90 degrees according to our construction. So in total, in the right angle BAE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle ABFE, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be a right angle, if not a square. So remember, quadrangle ABFE is right angle because it has 4 right angles. So here, quadrangle ABFE is right angle according to rule 5. But we also know that the opposite sides of right angle are equal to each other. So right angle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE is also 16. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF. But AE is H, therefore BF must be also equal to H. What is the length of the missing line segment FC? So the drawing, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC in total equals to DC minus DE minus EF. So FC equals to DC, that is 44, minus DE, that is X, minus FE, that is 16. So in total, FC equals to 44 minus X minus 16. So FC equals to 44 minus 16 is 28. So in total, this expression is equal to 28 minus X. So FC equals to 28 minus X units in its length. In the next step, I copy the right triangle BFC in a new page and replace the Pythagoras theorem in this right triangle BFC. So actually, this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared is equal to BF squared plus FC squared. BC is 25, therefore BC squared is 25 squared, that is 625. and it is equals to bf squared. Bf is h, therefore bf squared is h squared, plus fc squared. fc is 28.6, therefore fc squared is 28.6 squared. So in total, according to the Pythagoras one, we found out that 625 equals to h squared plus 28.6 squared. Here we open the brackets on this side of this equation 2, and find out that according to this equation 2, 625 equals to h squared plus 28.6 squared. 28.6 squared equals to 28 squared, that is 874, plus x squared minus 2 times 28.6, that is minus 56x. So here we subtracted 625 from this equation 2, and after we subtracted 625, in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have h squared plus x squared minus 56x, and we have 874 minus 625 is equal to 159. So in total we found out that 0 equals to h squared plus x squared minus 56x plus 159. Here we added 56x to this equation 2, and found out that here 0 plus 56x is 56x, so 56x equals to h squared plus x squared plus 159. But according to equation 1, we already found out that h squared plus x squared equals to 289. Therefore, we can substitute h squared plus x squared in this equation 2 by 289. We did it, and we found out that according to this equation 2, 56x equals to h squared plus x squared is 289, according to equation 1, plus 159. So in total, we found out that 56x equals to 289 plus 159 is equal to 448. So in total, according to equation 2, we found out that 56x equals to 448. Here we divided this equation 2 by 56, and finally found out that x equals to 448 over 56. 448 over 56 is 8. So we found out that x equals to 8 units instead. According to equation 1, x squared plus s squared equals to 289. If x equals to 8, it means that x squared must be equal to 8 squared, that is 64. So we can substitute x squared in this equation 1 by 64. We did it, and we found out that x squared is 64 plus 8 squared equals to 289. Here we subtracted 64 from this equation 1, and finally found out that 8 squared equals to 289 minus 64 is 225. So h squared equals to 225. Here we took root out of this equation, and finally found out that h equals to the square root of 225. The square root of 225 is 15. So in total we found out that h, that is the height of trapezoid ABCD, is equal to 15 units in length. Our mission is to find out the area of this trapezoid ABCD. The area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC, times the height, that is edge over 2. Because again, the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is AB plus DC, times the height, that is edge over 2. AB is 16, DC is 44, edge is 15, divided by 2. 16 plus 44 is 60, so in total this expression equals to 60 times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. So in total we found out the area of this trapezoid ABCD is equal to 450 square units. Okay, thank you very much.